like to derive the Navier-Stokes equation from a different point of view, from a more general point of view, just from Newtonian mechanics. This equation is about a flowing fluid. So we consider an element of the fluid, and we flow with the fluid. So we are in a coordinate system in which the fluid element is at rest. So suppose this is the x1 axis, x2 axis, and the fluid element is a cube in this coordinate system. This x3 axis. And the quantity we're interested in is the average velocity of this fluid element. So the equation, according to, if we just use Newton's equation, the acceleration is equal to the force acting on this element. So m times du dt, I use du dt because we are flowing with the element, must be equal to the force, which composed of an external force plus a force due to the neighboring elements. So this is the external forces. And this is due to neighbors. And you recall that ddt is the material derivative, namely the partial viscosity times u dot the gradient. So this is Newton's equation, and this is then a given external force, for example, the gravitational force. So all we have to do is figure out what g is. G is the force due to the neighboring elements. And we will work with things per unit volume. So rho is the density of the fluid, so that m is equal to rho times dx1, dx2, dx3. And F, the external force, is equal to some F times dx1, dx2, dx3. I use this small f to express force per unit volume. And G is equal to G times dx1, dx2, dx3. And then with the equation reduced to rho times du dt is equal to F plus G. And our object is to find G. Once you find G, you plug it into this equation, you have the Navier-Stokes equation. And to find G, we just analyze how the forces act on these volume elements can be expressed in terms of pressure and viscosity and things like that. So suppose the neighboring elements act on this cube without any shear in a static way, then all the forces are perpendicular to the six faces of this cube. If there is no shear force, then G is perpendicular to the faces of the element. For example, if I just, for clarity, I just illustrated with the projection to the x1, x2 plane, this element. And then the forces were perpendicular to these two faces. And they are, the force per unit area is the pressure. So if this is x1, this distance is dx1. So the force here per unit volume is P at 0, and this is P at dx1. And therefore the net force, G of dx1, dx2, dx3, this is the net force acting on this volume element in the one direction. This should be equal to the difference between these two forces of P at 0 minus P at dx1 times the area, which is the area of this face, which is equal to dx2 times dx3. Because P is force per unit area, right, of the area of this face, which is dx2 times dx3 in the other direction. And then G1 of dx2 times dx3 is equal to, you divide through by your P0 minus P of dx1 divided by dx1 times dx2 dx3. And then in the case of, in this case when the force is perpendicular to the surface, G1 is equal to minus dP dx1. And G2, same thing, is going to minus dP dx2. And G3 will be going to minus dP dx3. In short, G is equal to minus the gradient of P. And when you substitute this into the equation of motion here, you just get rho times du dt is equal to F minus delta P, where small f is the external force per unit volume. And this is called Euler's equation. Which we also derived from the Boltzmann equation in the zeroth order approximation. But here you can see that we derived it directly from Newton's equation. Of course, Boltzmann's equation was based on classical mechanics, so they're really from the same source. But this derivation makes it more general. You can apply this to any system, even if it's not a dilute gas. So now what if you have shear force? When there's shear force due to friction between elements, between fluid elements, then the force G will no longer be normal to the surfaces. On each surface, the force will be slightly off the normal. So it's more complicated. So if I draw this picture again, x1 and x2, x3 goes into the blackboard. Say the force acting on this side, before it was like this. Now it will be like this. It will not be perpendicular to the surface. And there's a vectors. I call it T1. It's a vector acting along the on the phase. T1 means the force acting on the phase T1. T1 because it's the phase whose normal is parallel to the x1 axis. So phase 1 means its normal is parallel to x1 and so forth. So this is called T1 because it's a force acting on this face, and this face, its normal is parallel to the x1 axis. And then I have T2 and so forth, T3 and so forth. And this is T1 at 0, and this is T1 at dx1. This is dx1. Now, since the T's are vectors, they each have 3 components. That is T1, T2, T3. They are vectors because they have a arbitrary direction. And each one has 3 components. So we just name the components. We call the components here P11, P12, P13. That is the first phase, the first component, second component, third component. So this is the force per unit area acting on the first phase along the x-axis. This is the force component, the force per unit area acting on the first surface, the second, the component along the y-axis, and so forth. So this is equal to P21, P22, P23, and this is equal to P31, P32, P33, and you have a pressure tensor. And the diagonal elements are the electrostatic pressures, are those that's normal to the surface. So you have a pressure tensor, and the diagonal elements is the hydrostatic pressure, and the off diagonal elements represents the shear force. So now let us now work at G1. Before, let me remind you, before, when there was only a normal hydrostatic G1 times dx1, dx2, dx3 is equal to minus dp dx1 times dx1, dx2, dx3. That's what we derived before, right? Now, let's compare. Now, G1, dx1, dx2, dx3 will have extra terms because this term comes from the balance of forces along the x-axis due to forces acting on the phase 1. But now there are forces along the x-axis coming from forces acting on phase 2 and phase 3 and so forth. And so this is equal to minus, instead of this I have dp11 dx1 plus dp, the force acting on the second surface on the first axis, dx2, because I have to take the difference along the two surfaces, plus dp31 dx3 times dx1, dx2, dx3. So this, in vector notation, is just G is equal to minus the divergence of the dyadic P. You recall the dyadic P. The ith component is d dxi pi dxj pij. And this dyadic notation applies to a symmetric tensor. P13 has to be P31. And then what the equation now becomes, now you have the Navier-Stokes equation. F minus P. And this is Navier-Stokes. So this, in a general way, shows you how, so all is very simple, just F is equal to ma. And then how do you generalize it from a case where the forces are hydrostatic, perpendicular to the surface, to forces that are not perpendicular? Then you have to replace P by a tensor, the pressure tensor, and you have the Navier-Stokes equation. Of course, we are not finished yet because we have to analyze the off-diagonal components in terms of the viscosity. So our next task is to express the elements in terms of observed coefficients. In this case, the viscosity. So the viscosity. So first let us restate that the diagonal elements of the pressure tensor are just the hydrostatic pressure. And since the hydrostatic pressure is isotropic, they are the same in all directions. P is equal to P11 is equal to P22 is equal to P3. Those are the diagonal elements. What about the off-diagonal elements? So we'll write Pij will be equal to this is delta Ij times P, that's this term, plus I'll call it P prime of Ij. P prime of Ij will then contain the information about the shear force. So the viscosity should enter in P prime. In the coordinate system chosen, P11 prime is equal to P22 prime is equal to P33 prime is equal to 0 by definition, because they all absorb into P. By this coordinate system, I mean the system in which the cube faces are parallel to my coordinate system. So it's this system. In this system, all the off-diagonal elements are 0 because they are by definition absorbed into P. But what about in a different coordinate system? In a general coordinate system, that is to be obtained by rotating the coordinate system. Instead of this, you have this. Let me draw it again. My cube is still here, but the coordinate system are rotated. This is a rotated coordinate system. We must have an equation that is good in any coordinate system. So we cannot say that to use this, you must choose this coordinate system, because this cannot apply to all fluid elements in the fluid. So you must have an equation that is covariant, that is good in any coordinate system. Then we observe that in any coordinate system, while P11 prime, P22 prime, P3 prime may not be 0, their sum must be 0. Why? Because this is equal to a trace of the symmetric tensor P. The trace is Pii, sum over all I. And this trace is invariant under coordinate transformations. The trace is invariant. Under rotation. So when you rotate it, each P prime may be different, but it may add up to 0, because the sum is 0 in one coordinate system and is independent of coordinate systems. Therefore, it must be 0. So now, we can define the p primes more precisely by expressing it in terms of the viscosity. The definition of viscosity comes from the following definition. For example, if you have a solid element here, and now you apply a force so that it is deformed into this shape in the next instant in time delta t. This is dx1, this is dx2, and let's call this angle d phi. The force, the shear force, F prime, along the one axis now, is by the minus a coefficient times d phi dt, where mu is the coefficient of viscosity. This you may regard as a definition of mu, or I can re-express it in a more familiar term. You notice that this distance is just equal to u1, the velocity in the u1 direction, times dt. And so this arc length, this way u1 times dt, must be equal to this side times this angle. So it must be equal to dx2 times d phi. Yeah, this is du1. Therefore, that is therefore du1 divided dx2 is equal to d phi dt. So we could also say that F1 is equal to minus mu times du1 times dx2. This is the first component. So this is part of a more familiar definition. It just says that it's called d1 because, let me draw another picture. You have this phase has a velocity, and it goes like this, and this velocity is u1, and this is x2. u1 changes from 0 to a certain value along x2. That's why I have du1 dx2. And F1 prime, if I draw a line here, is actually the frictional force. On the fluid element above. You see, if it's flowing this way, the fluid element is prevented by flowing with it with the frictional force in the opposite direction. That's why this is minus sign. And the presence of F prime means that the fluid above has a friction and it's not free to move. And so these two definitions are equivalent, and we'll now use this to work it into the pressure tensor. Actually, in the pressure tensor, if you consider how this general element moves, it actually moves this way. The element was something like this. In dt, it actually moves like this, of course. And there are two angles. There's a phi 1 here. There's a phi 2 here. And there were P12. P12 prime. There's a force along the x-axis due to the force from the phase 2. So this is actually equal to minus my d phi 1 dt plus d phi 2 dt. Because there are two deviations, you have to add them up. And this can be expressed in terms of equal to minus mu du2 by dx1 plus du1 by dx2. Therefore, in general, I can generalize this as minus mu dui by dxj plus duj by dxi. And this is true if I is not equal to j. When I is equal to j, you have to fix it so that the trace of this tensor is 0. So Pii must be such as to make the trace of P prime equal to 0. So now we can rewrite the whole thing because it's very simple to fix up the trace. I'll do it here. I claim that the answer is P ij prime is equal to minus mu dui dxj plus duj dxi. This term has to be proportional to delta ij. So it's minus 2/3 delta ij of divergence of u. To show that this works, let's check this. The trace of P prime is equal to minus mu times dui sum I going from 1 to 3 times 2, because I have two of them, and then plus minus 2/3 mu. I put I equal to j in some, so I get Laplacian. Pij is equal to Pij is equal to this plus 2/3 mu times 3 times delta u. 3 because when I put I equal to j in sum, I get 3. And this is equal to 0. So you can check. Because this is just divergence of u. So this cancels. The 3 cancels. So we have a divergence lesson. But in the Navier-Stokes equation, we need the gradient of the pressure tensor. So we need delta Pij, delta dxi. And that is equal to ddxi times p plus 2/3 mu divergence of u. This term takes us from the diagonal elements plus mu Laplacian of u. And now we plug this into the previous equation, you get the Navier-Stokes equation. d dt plus u dot gradient u is equal to f over m minus 1 over rho gradient of p minus mu over 3 divergence of u plus mu over rho divergence of u. And this is a Navier-Stokes equation. And we have derived it in general for all liquids, not just a dilute gas, from Newton's mechanics. Now, you sometimes when you see it quoted without this term, that is because in those cases they have assumed that divergence of u is 0. Is the divergence of u is 0 when there is no source or sink. In other words, in the fluid there's no source that adds to the fluid, and there's no sink in which drains out. In that case, the divergence of u is 0, and then you don't have this term. This is a very complicated equation, and its application is very wide, as I point out. It describes the weather. In weather prediction, you try to solve this. It describes the ocean, and it's a very important equation for studying the environment. And this equation is nonlinear. You see, there's a u squared term here, nonlinear, and it's very complicated. It has these divergences. That's a Laplacian of u. Needless to say, we cannot solve this exactly, except in some very special cases. And in general, it's difficult to solve it even numerically. So there's a whole discipline called computational hydrodynamics, and it's to study how to solve this equation numerically. So I'd like to just illustrate this in some simple cases what the behavior of this is. A very important case is incompressible flow. Non-viscous incompressible hydrodynamics. That covers a lot of cases. That is, you ignore the viscosity and the fluid is incompressible. That's a special case that's widely applicable, so I'll discuss that because that's a very simple special case. So the example is non-viscous incompressible hydrodynamics. without source. So this means that mu is equal to 0, rho is equal to constant, and divergence of u is equal to 0. This means non-viscous, this means incompressible, this means those sources. In which case, the equation becomes rho times d dt plus u dot gradient u is equal to, let us ignore the external force. This is just this case. This rho is a constant now. And incompressible means that dV dP is 0. When you change the pressure, the volume doesn't change, or the element doesn't change. And this means that gradient P is arbitrary. That's a peculiarity of incompressible flow. This delta P is arbitrary. It will adjust to anything you want depending on the boundary condition. That's a very important thing. Adjust to any boundary condition. To investigate some of the properties of this equation, let's take the curl of both sides. Take curl on both sides. On this side, you get rho is a constant, so you just get rho. The curl just commutes with this. ddt plus u dot gradient curl u is equal to the curl of the gradient, which is equal to 0. So this means the curl u is constant on a streamline. So if you follow the flow of the fluid, curl u is equal to 0. But since for most systems there's no rotation of fluid at infinity, curl u is 0 everywhere. Then curl u is everywhere equal to 0. Everywhere. So the consequence is that we have a flow in which there's no rotation, no vortex motion. So this means that u can be set equal to the gradient of some function because its curl is 0. And this phi is called the velocity potential. And the equation now becomes Laplacian of phi is equal to 0. So in an incompressible flow, you will reduce to solving a Laplace equation. And there's an analog, right? You could imagine that, so phi is like electrostatic potential. Without charges. Because this Poisson's equation without the charge. So it's like electrostatic in free space. And U is like the electric field. And in this way, you can qualitatively understand many kinds of flow. For example, if you have a sphere, and the liquid flows around the sphere in an incompressible way, what is the boundary condition? The boundary condition is that the liquid, the normal component of the liquid on the surface must vanish. The fluid cannot flow into the sphere. But we have such incompressible that can be satisfied, because gradient of P can adjust itself to whatever boundary condition. So it can always be satisfied. And so you are reducing solving a case in which you have a boundary here and you have some electrostatic outside. And I think most of you just know how to sketch. You would guess that the electric field would look like this as dipole. It's a dipole. It's a dipole geometry, so you would expect the U field would look like this. And this is what you will get if you do it in a liquid. So in many of these cases, you can just visualize it and know qualitatively what happens in the case of incompressible flow. In the case of compressible flow, things get complicated, much more complicated. So now I'll just make some general comments about the Navier-Stokes equation in general. If you look at this equation, what is important is this term is called the inertia term. And this term is called the viscous term. This is called the viscous force. And this gives you the inertial force. And the situations are very different when these two forces have different magnitudes. And there's a dimensionless quantity that characterizes the ratio between these two forces, and that's the Reynolds number. It's called RE usually. It's equal to, it's dimensionless, so it's equal to a typical, it's equal to the ratio between the inertial force to viscosity. So it's defined as, you take that term, you take a typical velocity u squared divided by typical length L. So this is u squared divided by 1 over the length. So this is this term. This is here, you take mu divided by rho times typical velocity divided by L squared. L squared because you have a Laplacian. So you come up with something like rho times u0 L divided by mu. It's a density times the typical velocity, typical length in the problem, and the viscosity coefficient. And the liquid behaves very differently for different regimes of the Reynolds number. Generally, if the Reynolds number is very small, much smaller than 1, you have viscous flow. The fluid is very viscous. Usually, if you have an object here, it will flow like a streamline around the object. By experience, when the Reynolds number is about 10, this becomes a breakdown, and behind here, vortices will develop. And then when it goes up just 90, these vortices will break loose and form what's called a vortex street. It streams along. This is a vortex. These are vortices. This is a vortex street. And then when it reaches, say 10 to the 5, you get turbulence. Here you get turbulence. And each of these regimes are very complicated, and of course, they require different techniques to analyze. That's why hydrodynamics is such a big subject. So the extreme high Reynolds case is turbulence. And the extreme low Reynolds numbers case is also very interesting. The extreme case this way. It's like swimming in a molasses. Imagine, suppose you would drop into a tank of molasses. How do you swim? You start to see your arms, you can hardly take, it's very viscous. In fact, it was shown that in a tank of molasses you cannot swim by flapping your arms. By moving your body, you just cannot go anywhere. And the only way to propel forward in a thick viscous medium is to turn something, as long as it's asymmetrical. And this is why bacteria develop flagella that turns when it swims in the viscous fluid, like the cell fluid. And that's interesting because that's the only way you can propagate yourself in a low Reynolds number case. And bacteria knew that. So this is a very fascinating subject, and it's a vast amount of things to learn, and computationally and theoretically. And this is where we shall leave hydrodynamics. And we'll go on to statistical mechanics after the rest.